Welcome to the University of Waikato. My name's Jonathan Scott. Thank you for taking time out of your schedule to come here. Boys, girls, high school students and space freaks. I get the honour of introducing Warwick Holmes, who's going to give us the talk. He insists that I should be brief because he thinks you don't care very much about what he is or where he came from. But I'll tell you very quickly, he was educated in Australia and then spent his working life, nearly 30 years in Europe, working on some of the most exciting science programs that you can imagine. It's the years you spent living in the south of France that I find it hardest to forgive you for. But he's here to tell us about, fairly obviously, probably the single most exciting piece of science that has been done in the last few years, and certainly the most exciting that anybody I know has been involved in. So, without further ado, Mr. Warwick Holmes, please will you tell us about Rosetta?
Thank you. Okay, good afternoon, students, and welcome to Waikato University. Today, I'm going to be telling you about this spacecraft, if my presentation begins. There we are. So the spacecraft is called Rosetta, and the comet we visited is called Comet 67P, which is what we call the 67th periodic comet that was discovered in orbit close to Jupiter and the Sun. So the fundamental question is, why do we want to visit a comet, and what is a comet? So first of all, a comet is a planetary body that's in part of our solar system. It's gravitationally bound to the Sun, but it's completely different than any of the planets or the asteroid belt that we're familiar with from other space missions. And the reason for that is the comets were formed more than 4.5 billion years ago, and they're basically the primitive chemistry of the very, very beginning of our solar system. The planets and the asteroids have been changed dramatically by heat. So the Sun and the planets were heated during their formation process, and that changes completely the chemistry. It's like burning a piece of paper and so all the planets that we've seen and all the asteroids are effectively burnt pieces of paper, but we've never seen an unburnt piece of paper, the chemistry of that. And this is what a comet is as part of our solar system. So this is a picture or a graphic of what the solar system looked like 4.5 billion years ago. But the difference here is that the Sun and the planets have already formed. And so this picture is a bit misleading because the real comets were formed even before the Sun and the planets were formed. So, just get this working. And so they were actually the material, whoops, I pushed the wrong button. Sorry. Okay. The cometary material is here on the outer reaches of the solar system. And this is where it's the coldest. And this is where the gases and the dust of the early primordial gas cloud that collapsed to form our solar system were first formed. They then stuck together and formed the planets, and the remnant leftover cometary material was then swept up by those comets and by the Sun. But the most important thing to remember is that this is the chemistry at the very beginning of the solar system, before even the Sun and the planets were formed. So why do we want to visit a comet? Well, the reason is we're trying to understand where does this original gas cloud that collapsed under gravitation to form this big swirling disk of gas and dust, and how that then became to form the Earth and then form us, intelligent life. So all of us sitting in the rostrum in this auditorium today were basically formed by dust from the collapse of an exploded sun, a star, that was brought together under gravity, formed the Earth, then water was brought by comets and some primitive chemistry to then form life and human life as we have here today. So this bombardment process, sorry, I'm having a bit of a problem here. This bombardment process is shown here in this video. So we have a comet coming in towards the early Earth, which was a red-hot ball of molten material which had collapsed under gravity and became extremely hot, like the magma from inside a volcano. And that's what the early Earth looked like 4.5 billion years ago. Then this process of cometary bombardment formed, and we've got our first tantalizing glimpse of what a comet was like when this meteorite hit Australia, called Murchison. It hit a place in a town near Victoria. And more than 100 amino acids were found in this comet. And amino acids are the building blocks of the RNA and DNA that forms human life. What is really scary is that on Earth, we only have 20 amino acids, and in our bodies. But this rock from deep outer space, from outside our solar system, on the edges of our solar system, carrying more than 100. So it was clear, and this meteorite they believe to be the core of an evaporated comet. So we got this tantalizing glimpse that there's some very exotic, very interesting chemistry going on in comets, and that's why we wanted to visit one. So what we found inside the Murchison meteorite, hidden deep inside, was these interesting chemicals called amino acids. And there's adenine and guanine, which are two of the primary amino acids which help to form the RNA and DNA chain of human life. And they were found deep inside this meteorite. So how do we get up there? So the European Space Agency decided to make the Rosetta mission. 25 years ago, they planned to make this spacecraft. It's solar-powered. It's the first time ever a deep space interplanetary exploration probe was made using solar panels. And we had to carry with us this little lander, a 100-kilogram lander, which was designed to go down onto the surface and make direct measurements in contact for the first time ever with a comet. And this is what the lander looks like free-flying. So it's about the size of a washing machine. It weighs 100 kilograms, and it has a tripod landing system which is designed to absorb the shock absorber when we touch the surface. So my role in this program, starting 15 years ago, was to do the building and the testing of Rosetta. And I worked on the program for 4.5 years, and it's the most interesting job I've ever had in my life. So I was involved in all the phases of the preparation and the launch of the spacecraft. And this was done in a place called French Guiana, which is a colony where Europe has access to a launch site. And we launched a large Ariane 5 rocket, which was used to carry Rosetta into the solar system to start the mission. And that was 11 years ago. So this is launched on the 2nd of March, 2004, just over 11 years ago. A complete Ariane 5 was used to try to put Rosetta on what we call a hyperbolic trajectory out into the solar system to catch the comet. Now, this is the control center in Germany, which actually then took over the control of the spacecraft. And for 10 years, Rosetta was flying around the solar system, and it went around the sun 4 times. And the reason we did that was we had to use the gravitational assist of planets to help accelerate Rosetta towards the comet. The comet was going 50,000 kilometers an hour faster than our launch speed, and so we needed to have an extra boost using the gravity of the planets of the solar system. The problem is that it took 10 years to do that synchronization to get that extra 50,000, so that was why the mission took so long to get to the comet. The signals for the first 8 years were sent from Australia. There's a big dish, a 36-meter dish made by the European Space Agency that's based in Australia, and it's a bit like that movie called The Dish, where Australia was using a big dish in New South Wales for talking to getting the video from the astronauts from the moon. Well, once again, Australia was used for a dish for talking to Rosetta. So, as I said, it took 10 years to get out there. We had to fly past the planets. One of the planets we flew past was Mars to get a gravity assist. And we went 250 kilometers above the surface, which is incredibly close, at 26,000 kilometers an hour, and we took a selfie. And that was using Philae, the little lander, which was strapped to the back of Rosetta, and we used it to test the cameras. So as we're flying over, this is the back of one of the solar panels, and you can see Mars below us. We also used it for testing all the cameras, and so there are 17 different colored filters we have on our scientific cameras, and so we used Mars as a test object. And we took these 3 different images in different colors to be sure that all the filters were working correctly. Then, en route, we went through the asteroid belt twice, and we went past an asteroid called Steins. And this was from 800 kilometers away, which is the distance from Sydney to Melbourne. 31,000 kilometers an hour, but it's only 6 kilometers across. So we have extremely powerful cameras to zoom in and to get this image as we were flying by at this incredible velocity. So when we finished that flyby, we then went past a second asteroid called Leticia. Oops. Show the video, there we are. So this was the flyby of asteroid Letitia, this time at 53,000 kilometers an hour because we built up more speed, again trying to catch the comet. Distance 3,160 kilometers away and 100 kilometers in diameter, so it was a bit bigger, but further away. So these were tantalizing glimpses of some asteroids that we flew past, but our primary objective was not the asteroids, it was to get to the comet. So this is all in passing to get out there. So this is the best photo we had of Letitia as we were flying by, and we used all our instruments to analyze that as well. Now, this is the detail of the comet orbit that we're trying to achieve. So this is Comet 67P, and when we first turned the spacecraft on after its hibernation, we had to turn the spacecraft off for 2.5 years because we got so far from the sun that even our solar panels didn't have enough electricity to keep the computers alive. So we had to turn off the spacecraft for 2.5 years and then turn it back on again to get enough energy to actually start the computers again. And this happened back in January last year, 2014. It took us 8 months to catch up to the comet and then slow down and go into orbit. So the first orbit was achieved in 6th of August, 2014. 12th of November was when we did the landing last year. So we're on the surface of the comet with a little lander fillet. And today we're about here. So we're getting into the active phase of the comet where it's being heated by the sun, and the closest approach is halfway between the Earth and Mars. And this is where the comet starts to evaporate, all the volatile chemistry on the surface and inside the comet, and we get to see 2 different phases of the comet for science. The dormant phase, where it's deeply frozen, and then when it starts to evaporate. So this today, if we're looking down on the solar system, this is a view of where the comet is today, 23rd of April. So we're traveling at 92,000 kilometers an hour. We're 387 million kilometers from Earth, 270 million from the sun. But this is what we call the speed of light delay. And that is, if we send an image, a photograph, from the orbiter back to Earth, it takes 21.5 minutes traveling at the speed of light to get to Earth, to be received by that antenna in Western Australia. And we've actually traveled a total distance of 6.9 billion kilometers. So this looping trajectory around the solar system 4 times to build up the speed, to get to the comet, we've actually traveled almost 7 billion kilometers. Now, this is the first images we had as we approached the comet from 1 million kilometers away, and this is our navigation camera that uses the positions of stars to calculate where we are. Can anybody see the comet? Okay, I'll help you. This, above the red dot, one of those stars is stationary, and that is the comet as we're zooming in. Above the red dot, there's one stationary star, and that's our first image we had of the comet. As we got closer, these were then the first images we got by stitching together a series of still photos, and we realized there was something very, very strange going on. That was not what we were expecting to see. It's a very unusual shape. It seems to be 2 comets for the price of 1. And in fact, the science that we're doing right now, we're trying to prove that, to see if it's 2 bodies or 1 body that's eroded into a funny shape. So those are our first images of what the comet looked like as we started to approach. So it didn't take very long for a journalist and known scientist to say, well, it looks like a rubber duck. And in fact, I have to agree. It does look like a rubber duck. So we went all that way to discover a duck in orbit around the sun. So then we spent our time taking a series of photos of high resolution around the comet, mapping the surface and trying to understand the science and the physics of the comet. What is extremely important to understand is that this comet is absolutely pitch black, the color. It's like the toner cartridge powder that you get from a photocopier, or it's blacker than coal dust. Now, to get these images, we have very, very special cameras which can enhance the brightness and the contrast to see the surface. And we have also got color, so we can actually enhance the color. We add in the color from anything that we can find from the different filters. But only 6% of the light gets reflected from the surface of this comet, and because of the distance we're away, we get 1/10 of the amount of sunlight. So effectively, only 0.6% of the light that hits this comet is reflected into the cameras. And if we were standing right here beside it in front of us, we wouldn't see it. So we have some incredibly powerful cameras to get these images. And so we were going into orbit around at different altitudes and mapping the surface to try to understand what the shape of the comet was. And this is, again, another photo from Philae, the lander, using its cameras, testing its cameras in the vicinity of the comet. And we got this fantastic photo looking at the back of the solar panel, again, with the comet in the foreground. And this is from a distance of only 16 kilometers. So then we started taking a series of very high-resolution images of the surface, and every photo we took, we saw strange things we've never seen before. What you have to appreciate is that this surface is made of frozen gases frozen carbon dioxide, frozen carbon monoxide, nitrous oxides, methane. And these are not boulders, these are clumps of frozen gas and amino acid and carbon chemistry, exotic chemistry that we've never seen even on the Earth under natural circumstances. So even though this looks like an Earth-like terrain, it's anything but. Not one part of this surface is common to planet Earth. So it's very, very unusual shapes, and we started realizing, well, we have to find a place to put the lander down. And everywhere we looked, there were crevices and cracks and plates and cliffs, and even here, these little craters here are not formed by impacts or by any or volcanoes. It's actually formed by the evaporation of gas from inside the comet. So these are sort of like gas volcanoes, I guess you'd call them. So we managed to stitch together about 20,000 images have been taken so far, possibly even more now. And we were able to stitch them all together and make these animation sequences to understand the best trajectories for trying to do the landing and for getting science from the surface. And so these incredible high-resolution images. Now, these have been generated from 500 million kilometers away from Earth. Oops, sorry. Oops, okay. Sorry about that. And we started to realize everywhere we looked, there are strange features. Now, looking down on the comet again from the orbiter, we found what looks like a well. A typical cylindrical hole has been drilled effectively straight into the comet. And we're trying to understand, well, what is that? So then we increased the amplification of the contrast of the images and the brightness, and we realized that these were holes where gases and dust were evaporating from inside the comet. So like it's a volatile hole where all the gas jets come out to form the tail of the comet. And then also here's another one where we can see this sort of molten residue of what is effectively a frozen gas, which has turned into a liquid momentarily during its evaporation process as we came close to the sun on a previous orbit. So there's all this evidence of strange oozing gases and liquids, but all they're frozen gases at very, very low temperatures. The temperature of the surface of the comet is on average about minus 70 degrees Celsius. This is a side-looking view of one of these holes, and it looks like there's lots of little golf balls on the surface here. We call them goosebumps. And so we're trying to understand, well, what is the mechanism that forms that strange surface feature on one of these vent holes? With these unusual wind-blown features as well, where it looks like these are sand dunes. Well, the comet has no atmosphere, so where does the wind come from? And so we think that when it goes past the sun, there's an evaporation is formed, which forms a temporary atmosphere, and it blows some of the surface around, just during the evaporation of the volatile gases and chemicals close to the sun. But we couldn't understand why are there sand dunes, apparently sand dunes, on a freezing cold comet. Likewise, we have what we call these wind tails behind what look like boulders. Again, these are frozen clumps of ice, we believe. But we've got these features that look like there's been a wind blowing in this direction. Again, a temporary feature caused by, we think, the evaporation of the comet as it goes past the sun. Most interesting of all, we found there was a crack in the neck of the poor old duck. Okay, so we think it's possible that the head and the body may separate. This has happened before in other comets that went close to Jupiter. A famous comet called Schumacher-Levy broke into 22 pieces as it went close to Jupiter. There is a possibility that 67P may break into two pieces. The head and the body may separate. If it does, and we're close to the sun, the lander may switch back on again, and we may actually be able to record the noise of the comet cracking, because we have 3 microphones on the feet of the lander, which we're using for seismology, but we'll also hear noises being generated by the comet itself. So it is indeed a comet. What we're expecting to see are gas jets and evaporation and of dust and ice. And as we get close to the sun, it starts to evaporate. We lose about 5 to 20 meters of surface, of the surface of the comet will be evaporated by this trajectory past the sun. Now the comet's about 4 kilometers long, 3 kilometers wide, and 2 kilometers high. And so it's going to take a long time for the comet to evaporate to nothing, but it will never completely go because there are some elements and molecules inside the comet which will never be evaporated by the sun, and so there will be a sticky black residue left over, a bit like the Murchison meteorite, which will be left behind. But it is indeed a comet. As you can see, these images now, as we're getting close to the sun, the comet's becoming very active, and the rotation rate of the comet, which is 12 hours and 40 minutes, is slowing down, because these gas jets are acting like little jet engines, little thrusters, which are slowing the rotation of the comet as we get close to the sun. Only by fractions of a millisecond, but we can actually measure that, and we can actually see they are slowing down the comet very slowly. one of the theories was Godzilla must be making the gas jets. That was one of our scientists came up with that theory. Now, one of the most interesting discoveries was there's a plasma field around the comet, which means that as it's evaporating these gases, the sun ionizes the gas and forms what we call a plasma. And as it interacts with the solar wind, we get this unusual oscillation. It's basically that the comet is singing, in a sense, using its plasma field. And so I'm going to play to you a noise that we recorded when we multiplied the speed of this oscillation about 10,000 times, and we can then actually hear the signal. Okay, so that rapid ticking sound is the oscillation of the plasma being pushed in and out by the sun as the evaporation of the gas from the surface is changing. And as it's rotating in the sun, and we're changing our orbit with the orbiter, we get different frequencies. So it's a very unusual sound, and some musicians in Europe have actually made a song using this as the background sound. Okay, so after we mapped very carefully the surface, we decided to start looking for a landing site. And this was a very, very difficult job because the shape of the comet was unusual and the surface was extremely rough. So we started analyzing all the best places in terms of flatness, in terms of slope, in terms of sunlight, and in terms of the minimum number of boulders. I call them boulders, but they're not boulders, they're frozen blocks of gaseous ice. And this turned out to be the flattest area for us to come down on. This is on the head of the comet. And we stitched together, again, many images to form a 3D view as we're flying over the surface of the landing site, which I hope is going to start. Here we are. Okay, so this is, again, we've stitched together many thousands of images to create this animation sequence of looking across the surface of the landing site for the best approach trajectory and the best place to do science. And that, believe it or not, is the best landing site on the whole comet, which is still not very nice. 50% of that landing area was unsuitable because of slope, sunlight, and these boulders, but that's the best we had. So we went all that way. We were determined to make a landing anyway. So this is now the landing sequence that we wanted to try to attempt with Rosetta and Philae, the little lander that was strapped onto the back of the spacecraft. And the idea is that we fly over the comet, and at exactly the same speed, we push the lander, Philae, off the back. And so the effective speed of the lander is 0 over the surface, and it's just hovering and is gently taken down at about 1 meter per second onto the surface. We were 20 kilometers above the surface, and it took 7 hours for us to come down. And we deploy the landing gear, the antennas, and some scientific instruments. And the idea is we're meant to land at about 3 kilometers an hour and fire 2 harpoons into the surface, these red wires here. Now, unfortunately, that didn't happen in exactly the way that we'd planned. And I'll show you the consequence of that. So this is the real sequence during the deployment. This is the little lander popped off, and we're taking images of this from the orbiter as it was coming down onto the surface. Now, what's important in this image is to understand in the background is a full image of the comet. But you can't see it because it's as black as what I was explaining to you before. But to pick up the lander with the sunlight shining off it, we were focusing on the brightness of that rather than the image of the comet. But it just shows just how ridiculously dark the actual comet is in reality when we're focusing on an object which we're familiar with. And so this is the descent sequence. All of this was happening at about 600 million kilometers away from Earth. Each of these images takes 28 minutes to get to Earth at that time. And the way that we knew we touched down is on that tripod, the feet of that lander. We've got these 3 microphones we use for listening to the noise of the seismology we're performing on the comet. But we also use it to know when we actually touched down, and we got this sound. And that was it. That was us hitting the surface. So we knew we hit something. Okay, so this is the landing we wanted. We wanted in a large, flat, open area. We've got 6 cameras around the edge of the lander, and what we wanted to, or expecting to see was half sky and half land, or surface of the comet from these 6 different cameras. So this is an image looking down at the landing site, and we realized that something had gone wrong. So we're 20 kilometers above the surface of the comet. And we're looking down, and that green square was where we were planning to hit. But this shadow shows a dust cloud before and after the lander hit the surface. So we could see there's like a little puff of dust, but there was no lander there. So we realized we had a problem. It hadn't stuck to the surface. So we got within half a meter of where we wanted to, which is an incredible achievement from 22 kilometers, but the lander wasn't there. So one of the other flight dynamics people realized that in this image, we can actually see a tiny little pixel here, which is brighter than the rest, and a darker one, which corresponded in velocity to the rebound speed or direction of Philae. So in this image, we see the dust cloud as well, but we also see little Philae and its shadow on the surface of the comet bouncing off in this direction off to the right. I think this is one of the most incredible images in spacecraft exploration history, to catch that little lander moving off the surface of this incredibly dark comet. And that's what we managed to catch. So we knew we had moved. We were bouncing, we were rebounded, and we were back off the surface again. And so then we did, this I think is the most incredible image. This is where we took a sequence of photos of the lander coming down. This is before we touched down, drifting across the surface of the comet. And this is our touchdown point. This is the before and after, where you can see the three little tripod marks where we had touched but bounced off. But in that same time, at 1543, we looked around and we found this little white dot here, zoomed in, and there was the lander moving off the frame. So this is, I have to say, this is the most incredible image I think you could ever see from a spacecraft exploration history, because it was taken outside the asteroid belt. And each one of these images, like I said, took 28 minutes to get to Earth, and this surface is blacker than coal dust. So just technically, in every sense, getting these images and to find the little lander bouncing off, I think is just an incredible achievement. So this is what happened. We bounced up, we hit the crater, the edge of the crater, changed direction, and went off and landed in this dark valley here. And this is the problem, because the little lander has solar panels around its surface and is designed to use the solar power of the sun to recharge to do some of the science at a later phase. We had a battery which could do 3 days of science when we first touched down, but we wanted the solar panels to then recharge the lander again. So we realized that we landed somewhere in this shadowed region here. As I'm speaking to you today, we still have not found the little lander on the surface from the orbiter, but it's definitely on the surface somewhere, because these are the images that we took. So this is these 6 panoramic cameras I mentioned to you before, and this is their orientation around the lander if it had landed in the correct attitude. So camera number 1, we saw a very, very dark image of what looked like a wall, but instead of half sky at the top here and half surface of comet at the bottom, we got a whole image, which we weren't expecting. Camera number 2 was looking out into deep space. This is a reflection off the camera lens, and this is one of the antennas used for one of the science experiments. But we were looking up straight out into space, and we were certainly not expecting that. Camera number 3, we see another wall, this time sunlit. So that's good news, together with one of the feet of the lander on the surface. Camera number 4, again, a sunlit wall. Not quite in the orientation we expected, but at least we're getting a close-up image. 5 was extremely dark, and 6 was also extremely dark, but we could see at least a surface. So then by putting all those together, we put cameras 3 and 4 together to get this better image of the wall, this sunlit wall on the surface of the comet with the lander leg. And then we added the color and the depth of field to the image, and this is the most realistic image that we've got of the surface of a comet. Again, with chemistry that we've never seen before. So, analysing those images, we realised that after all the bouncing, poor little lander had landed side on in a little crevice with shadow on one side and sunlight only on this other wall here. So it's not the best landing, but at least we're on the surface and we are doing science. So, that's the end of the presentation. The most common question I get at the end of this is, how can a student, a New Zealand student in this case, work on Rosetta? So these are my answers to that question. You have to be a very ordinary student, because I was. I wasn't an A-stream student, I wasn't a university medal winner or nothing like that. A very ordinary student, but I was absolutely determined and committed to working in space. And to do that, I had to focus on science, technology, engineering, and mathematics subjects. I mean, that's a given. You have to do that to do this kind of work. You have to have good teachers, like Professor Jonathan Scott, who did the introduction today. And if it wasn't for Jonathan, I wouldn't have been able to do this work. You must have good teachers. and you have to work hard yourself, and you have to go to a good university, like Waikato. Okay, so I'd like to thank those people who helped do the presentation today, organise the presentation for me today, and this is, for legal reasons, I have to say who made all the photos for me, okay? So that's the end of the presentation. So now, I would like to introduce John Little from the Science Department here at Waikato, who's going to show you today how we're going to cook a comet. Now that's a bit misleading because there's no cooking involved, it's actually extremely cold. And what we're going to try and show you is, here on Earth, all the science and the measurements that we've taken so far with Rosetta and Philae, we're going to try to create, as close as we can here on Earth, the equivalent of what a comet will look like. And that's the chemistry, the materials, the temperature, and its appearance. So I'd just like to bring John Little now, I think. I'm not quite sure where he is. He's probably preparing the chemicals. What it involves is we're going to be putting some crushed dry ice and water ice together and some charcoal to make the color, which is very black. And at the end of the presentation, when you're leaving, we've actually got also a lot of chemicals which are the exotic chemistry, carbon chemistry, which is been identified by what we call mass spectrometers on the surface, and they're very smelly. A lot of the chemicals, there's methanes and formaldehydes and butyric acid, which all have a smell. So because we've been able to identify those chemicals, we're going to mix them together today, and you'll be able to actually effectively smell the same chemicals which exist on the comet. So by putting all those together, we'll give you the smell, the sound, the sight of what comets look like. Okay. So I'm just wondering where is our scientist?
We've got some questions while
Okay, good point. Are there any questions from the presentation so far? A bit difficult to see. Yes, up the back there. I think we've got a microphone that's going to... the question was that I mentioned that the comets are losing mass as they go past the sun and evaporating. That's absolutely correct. The growing phase was at 4.5 billion years ago. That was when the comets were growing, when this gas and dust cloud first formed, and they were flying around in orbit around the sun and were scooping up this gas and dust from the formation of the very beginning of the solar system. But as soon as it got close to the sun, the process now is evaporation only. There might be a few tiny little pieces they might scoop up in their orbit around Jupiter, up towards Jupiter, but the overwhelming mass of the comet now is being evaporated by the sun. And the reason we're close to the sun now is because Jupiter helped capture the orbit of the comet and bring it in. You need two bodies to capture a comet, the sun and Jupiter. So unfortunately, 67P got too close to Jupiter at one stage and it got drawn in. And so because of that, we're now in an evaporation phase. So poor old 67P is only going to disappear. It will never completely disappear because the really, they call them refractory elements and molecules can't evaporate. They will be left behind as a gooey, sticky black rock material. Okay? Question?
If the comet is losing mass, how can the Rosetta stay on there?
That's a very good question. Okay, even though it's very gentle evaporation, even though the gas and the dust and the ice underneath the lander will be slowly evaporating, that's very true. It's a very, very gentle evaporation in that locality of the little lander. So it's heavy enough to resist any gas directly evaporating underneath it. But it certainly will always be on that surface. Unless we landed right on one of those vent holes, that could have been a different story. We've actually got it's an image I didn't show, but we've got an image looking straight down from the lander as well, and we're definitely not on one of those holes, because if we were, we would have gone inside the comet, right, and we would have no images at all. So luckily, we're not on a vent hole, and so therefore that evaporation will be very gentle. Okay, now I'll just introduce John Little here, who's going to help us make a comet today. So I'll just be narrating as John's doing all the work. So the primary ingredient that we have is frozen carbon dioxide gas. So we call it party ice, which they use for sometimes delivering cakes. And frozen carbon dioxide gas is one of the most important frozen gases on the comet, together with water ice, which is the majority of the material on the comet. And then we have all these exotic carbon chemistry. We have these amino acids, we have formaldehyde, we have methanes, we have alcohols, we have sugars even as well. And so today what what I'd like John to try and help me do is to make an analogy, an analog of the comet. So it's extremely cold, and we'll be crushing this ball of ice together with charcoal to make it as dark as we possibly can. So in principle, the comet should be completely jet black, as black as we can make it, so that hopefully if we hold it up, you shouldn't even be able to see it, but of course you will. So it's cold, it's dark, and it's evaporating all the time, so you can see the vapor of the carbon dioxide gas coming off. Now what we were going to do is try and sprinkle the smelly chemicals on as well. But in fact, we didn't do that because we realized that you won't be able to smell them out there in the audience. So at the end of the presentation, as we're going out the door, there's some glass jars with some cotton wool inside. And we then use that to create the smell. Okay, so John. Well, I'll just narrate as John does all the work. So he's going to be pouring in the frozen carbon dioxide ice. Already we've put some charcoal inside with some water. And as you can see, it's extremely cold, which is the temperature of the comet. Okay, so that's the primary ingredient, together with water ice, which is in there as well, and some liquid water. Now we have to try and mix all that up, and then crush it into a solid ball to hopefully form a solid mass, which we can then hold up in front of you as a steaming cold black comet. Now this is actually very difficult to do. This is why I've asked John to do it. So if it doesn't work, it is actually very difficult to do. I just hope we can do this. If not, we'll just leave it in the bowl and then we'll show it to you separately. But if we're really lucky, this will all stick together. So during the presentation today, I've tried to give you images and the sound of the comet from the plasma field. Here we've got a physical example and the smell outside. So all the senses of what a comet is like, we're hoping to present to you today. So just hoping it all sticks together. Now we're going to try and take it out of the plastic bag, and if we can, we'll hold it up to you to show you. I can try and pull it off. You got it?
Yep.
Okay, just show the back side. That's it. Okay, there we are. Okay, now I have to say that is the absolute best example I've ever seen. Okay, so I've seen. So you can see that it's evaporating in the temperature of the surrounding atmosphere here, and we might get the bowl ready again just to catch it. There we are. But the important thing to see here is it is evaporating. It is volatile, and it's very cold. These are the frozen gases which are evaporating in just the ambient temperature of our hall here. But as the real comet gets close to the sun, exactly the same process occurs. The difference is that as the solar wind from the sun actually pushes this evaporation and plasma and gases away and forms the big tail that we're familiar with in normal comets. But this is an excellent example of how dark and how cold and how eerie the comet really is. And I think that's an excellent job. Thank you, John. You can hear it crackling. It's, it's a very, very eerie thing. I think that's excellent. So, any questions relating to that? A bit difficult to see.
Were there any unexpected substances that you found on the comet? Anything that you weren't expecting it to be
Very
made
good
out
question. Well, we are expecting to find some very exotic amino acids and carbon chemistry. So what we've done is we've taken a mass spectrometer and a gas chromatographer up with us to identify any molecules at all. So we've taken up instruments to try to find unexpected chemicals. At the moment, they're doing the measurements as I'm speaking to you, and they won't be releasing that information until later on towards the end of the mission, when they've done all the science and all the measurements, and then they'll write one big scientific paper. But certainly we've got the tools for finding unexpected chemistry, and yes, we certainly expect to find those, a bit like this 100 amino acids that were found on the Murchison meteorite. Now, they can only form in very cold, very dark places on the outer edge of our solar system, where there's no ultraviolet light, there's no heat, there's no disturbing forces to ruin that chemistry. So, as 67P is from that same region, we're expecting on the surface also very weird, exotic carbon chemistry, which forms this black color. So to answer your question, we haven't announced anything yet, but they are certainly finding unusual things, and that shall be announced sometime soon. Okay? Any other questions?
Your little antenna on Philae had little whippy things hanging. What on earth was that?
They were the Kevlar fibers that were holding the antennas in, and we cut them with a little thermal knife. So there's a little blade. We heat the blade. It melts the Kevlar, and the wires spring open. So it's a very reliable mechanism for holding things in. And when you want to release them, you just cut a wire, and it pops open. So they were the antennas that we use for what we call the CONCERT experiment, which is what we call RF tomography. And it's a method of taking an image inside the comet. So the little lander is on the surface of the comet. The orbiter goes around, and we can actually transmit a signal through the comet and get an image inside. A bit like when you go to the hospital and you get your CAT scan through your head. Well, we're doing a CAT scan of the comet, and those antennas were used for transmitting that signal. Yes?
Wouldn't the lander landing after you're in the shadow, didn't you have to reschedule your experiments for when you're close to the sun and you're getting more energy?
Very good question. Absolutely. The question is, do we have to reschedule our science because we landed in the shadow? Well, absolutely. When we realized that we had landed in the shadow, we had 3 days of science using a pre-charged battery, which was going to drive the 10 instruments on the lander. And so we had a schedule for that when we were in the open of what we thought was going to be a nice open sunny plain. When we realized that we had tilted over and something was wrong, the instruments which drill into the surface of the comet were scheduled last, in case it pushed it over and made the situation even worse. So we did reschedule all the non-contact science experiments at the beginning until the very end, and then we did the drilling, and that luckily didn't make the situation worse. But now, because we're in the dark, in this 25% of the sun is all we can see now. 3/4 of it is missing because of this shadow. So we will reschedule now completely the science for the second phase to use low-power instruments first, and then we just keep on doing as much science as we can until we drain the battery again. If we're lucky, it may recharge again. So there's a lot of unknowns because of the strange situation that we're in, but they will certainly adapt the science to make the most of the shadow that we find ourselves in, yeah?
Will the presence of the satellite orbiting the comet change the trajectory?
The question was, does the presence of the orbiter, Rosetta, around the comet change the trajectory? In fact, no, it won't, because we're in orbit around the center of the gravity of the comet. So its trajectory around the sun won't be affected in that sense. Also, the mass ratio, the comet weighs 10 trillion tons, okay, which sounds like a lot, but in fact, in planetary terms, that's nothing. It's an incredibly small object. The density of the comet is less than water. If we were to take this and put it into water, it would float. And so it's got half the density of water. So it's actually a very fragile, very low density, very porous material. Like the comet here, it's very porous. It weighs 10 trillion tons, and the Rosetta weighs 3 tons. So we've got a 3 to 10 trillion ton ratio. We might be slowly wobbling the orbit as we're going around it, but its trajectory will remain the same around the sun. Okay. So any questions relating to the coursework to get into this kind of work? Because as an engineer, you have to do science and engineering and mathematics, and that's, people think they're sort of geeky subjects, but for me, it's been the most exciting job I've ever had in my life. And when I come and talk to other students that I were at university with who did law and financial services, these kinds of things, they say, well, we always thought that engineering was geeky and science was geeky, but this is science and engineering. And this is necessary to do these kind of interesting missions. So I just want to encourage you all to look at the STEM subjects when you're at school and think about doing that when you come here to university, because it might seem boring, and I was thinking that when I was doing these courses too. But for me, I had an objective, and that was I wanted to work in space, and I knew I had to use mathematics and physics and chemistry. So once you've got a goal, it really helps you to do that study and to do what you think is the geeky subjects. It's not geeky. It's actually the coolest work I've ever could have imagined that I could have done in my life. So that's why I'd like to try to inspire you to think in those terms. Because a lot of people, I think, today think it's not so interesting. But with this sort of work, I think you can agree it is actually pretty cool. Okay, any other questions? Yes. Well, we're hoping to hear noises with Philae on the surface. We've got these 3 microphones and 3 speakers, and we actually send pinging sound. It's like seismology. We actually ping into the surface and we look at the reflective layers inside. But because the microphones can also listen in a passive mode, we hope to hear maybe cracking as the heat of the comet is being activated by the sun. It's maybe expanding, and there's a crack in the neck. I mean, we can see that. And that's a pretty substantial crack. It's hundreds and hundreds of meters long. And so we expect to hear cracking maybe in the same way. The problem is we have to turn the lander back on again. Hopefully we get enough sunlight to reactivate, and the first thing I'm sure they're going to do is turn the microphones on. Yes?
This might sound like a stupid question, but how do you hear sound on the comet if there's no atmosphere?
That's not a stupid question, that's a brilliant question. We are in a hard vacuum. There is no transfer of sound through the non-atmosphere, because there is no atmosphere. So here on Earth, you can hear my voice because of vibrations in the air and the sound waves. These microphones are in contact with a solid surface, and it's like when you're putting your ear against a floorboard and you're tapping the floorboard. You're hearing this sound going through the physical floorboard. Okay, so in the comet, we're hearing sounds go through the ice. Is useless. It won't do anything. And they're the ones which will hear, they're vibrations in the solid body of the comet. So that's what we're listening for. Okay? Yes? Okay. Okay, well, the spacecraft, the whole mission was done by the European Space Agency, which is a consortium of 20 European countries that agree to put taxpayers' money together at a certain small amount. They put all that together to make these missions. Rosetta took 25 years to plan, to design, to build, to launch, and to operate to get to the comet today. A 25-year mission. That took about 2,000 people in total. Those are the people that designed every single circuit board, every single structure of the lander, the rocket, the operations team. It took 2,000 people, roughly, to do that work. The team I worked in, the final building and the testing and the launch, is about 40. It's actually quite a small team. But it's a very complex spacecraft, and you just have to learn how the thing works. So one of my primary roles was testing the software of the spacecraft, which had an enormous amount of intelligence. For it to survive so far from Earth, it had to think for itself. Because if something went wrong, by the time it told us, for the furthest distance, it was a 50-minute speed of light delay time. So if something went wrong, it would take 50 minutes to tell us, and 50 minutes for us to send a signal back to stop the problem. 100 minutes is way too long for some problems. So we had to build in a huge amount of intelligence into the spacecraft in terms of software. And my job was to test that software to be sure, is it doing the right thing? Is it making the right decisions? And so that was a team of about 40 people doing the testing and the building and the launch, because there's only so many people you can get in a clean room around a spacecraft. So that was the size of that team, but in total, about 2,000 people. It cost 2 billion New Zealand dollars, but that was over 25 years. And when you think in per kilometre, that's about 30 cents a kilometre in terms of the 6.5, which is a lot cheaper than a taxi, okay? So it's not that expensive. Okay, any other questions?
I understand beryllium is a metal used a lot in spacecraft construction. Can you tell me the role beryllium played in constructing this stuff?
Sorry, what the material is?
Beryllium metal.
Beryllium, yes, beryllium is used. It's a very, well, it's an element, of course, but it's a very toxic element, and you've got to be extremely careful. Beryllium's very brittle and very light and very tough. It's one of the best materials for mechanisms in space. The problem is it's very carcinogenic, and if you're machining or cutting beryllium and there's any kind of material that gets absorbed into your lung, you're in trouble. So that's actually one of the most toxic and hazardous materials, but we do use beryllium in the spacecraft. Most of the spacecraft is made of carbon fiber panels with honeycomb aluminium layering. That's to form the structure. But all the other electronics are the same as the circuit boards we have today in our computers, but they're built using very robust design and components which have been what we call qualified for space, which is for radiation, an enormous thermal range. For example, the spacecraft we built had to survive a temperature range of 300 degrees Celsius. So you can imagine if I say, well, does your TV work in your freezer? Okay, so you put your TV in the freezer at 0 degrees. Yes, it works. Okay, now put it in the oven at 300 degrees Celsius and tell me, does it still work? Now, this is what Rosetta had to contend with. We tested it from minus 170 degrees to plus 150. And that's the thermal range that the spacecraft went through in its 10-year flight. We went in slightly close to the sun to then go out because of the complex orbital dynamics. And then we went out to Jupiter, which is where the sun intensity is 1/25th of what we have here on Earth. So there's enormous thermal range. The spacecraft had to survive. And that's one of the biggest problems. So the materials are one thing, but there's many other issues which the materials have to be chosen to survive, and one of them is big temperature range. Good question. Another one at the back there?
You mentioned that the European Space Union was conducting this experiment. Are there any other interesting experiments we should be keeping an eye on from the European Space Union?
European Space Agency, it's called.
Agency.
Yes, well, look, they have many programs which are running in parallel. They have different divisions. There's the Science Division, which made Rosetta. There's the Manned Spaceflight Division, which does the European astronauts to the International Space Station. There's the Launcher Division, who are designing the rockets. There's the Earth Observation Division, which does the remote sensing, which does taking images of the Earth to improve our environment. So there are several different divisions in the European Space Agency which are all doing projects in parallel at the moment. But they choose them on the scientific merit and what is the most needed technology for Europe to develop its space industries. The whole idea of ESA is that they do the difficult stuff, and once they've got something working, which is very complex, they then let European space industry then commercialize and use that technology for their own purposes. So it's the idea is that you use this combination of government money to do really complex, really difficult things, but they do it really well. Okay. Any other questions? Yes?
How do they expect that the knowledge that they gain from this mission will actually benefit humankind?
Good question. Okay, so it goes back to the beginning of the lecture. Why do we want to go to a comet? What's the reason we go for these 10 years, 2 billion euros to go all the way up to this comet, and what are we expecting to find? Well, when I showed you that image of the comet coming into the red-hot Earth, okay, that's how the Earth first looked like 4.5 billion years ago. It was red hot. There wasn't any water on the surface of the Earth. But if you look today, there's 70% of the Earth is covered in seawater, or water. And 2015, you ask any geologist or any scientist, where did that water come from? They actually can't tell you. Nobody knows definitively where all that water came from after we had a red-hot Earth. That seems crazy that in 2015 we actually don't know the definitive answer to that question. The most popular theory is that it was what we call a secondary cometary bombardment. 1.3 billion years after the Earth formed 4.5 billion years ago, the surface of the Earth had cooled down enough that this secondary phase of comets that came in cleaning up this disk of material left over from the formation of the solar system, predominantly by, again, Jupiter, Saturn, Uranus, and Neptune. The big gas giants brought in the leftover material in towards the sun, either got swallowed by those planets or got thrown out. So that the stuff that came in towards the sun hit the Earth on the way through. And if you look at the moon today, you can see that it was obviously a solid body. It's solid and it's covered in millions and millions and millions of craters. Okay, so something happened after the moon was a solid form body and there was a secondary bombardment. The same thing happened to Earth, right beside the moon, but 6 times more. It has 6 times the gravity. We don't see the craters today on the Earth because of weather, which smooths everything out, and plate tectonics, where that smooths out all the craters. We don't see that anymore. But what we do see is the water that got left behind. So they believe that the water from all the oceans came from this secondary cometary and bombardment phase, which is full of water ice that filled up the oceans. But the black, really interesting carbon chemistry, which is also all throughout the comet, these amino acids, also help to seed the building blocks of life in the ocean. So when the oceans formed, 200 to 300 million years after the oceans formed, the first algae was found. And that's a ridiculously short period of time for just a sterile body of water to suddenly create algae. It just doesn't work like that. It happens today because we've already got the algae. But that process of those building blocks forming life in terms of cells and molecules and the cells of life to form the algae was very, very fast. And so they think that the water came from comets. They think that the amino acid chemistry came from comets that helped start very rapidly, 200, 300 million years, which is rapid, the formation of life. So the reason we want to go out to comets is to see, do we see that water with these deuterium-hydrogen ratio, which we think is a way of telling you that the water came from comets, together with mass spectrometry to look at the carbon chemistry, the primitive carbon chemistry, the amino acids that also help form life. We have to go there to say, yes, we can see that material is there. The only way we can do that is a direct measurement on the surface of a comet, which we're doing right now. Okay? Any other questions? Yes?
Do you at the European Space Agency work with other space agencies?
Oh, yes, indeed. The question is, does the European Space Agency work with other space agencies? Absolutely. They've got probably one of the best working relationships of any of the big international organizations. 3 of the 21 instruments on Rosetta were built by NASA. We use the NASA dishes, these big 70-meter dishes that they have in California and some in Australia. We use those as well to help find the signals when Rosetta was waking up. So there's extremely good cooperation between NASA and ESA. There's JAXA, which is a Japanese agency, which we're doing a spacecraft now, which is going to go into orbit around Mercury. That's ESA with the Japanese space agency. With the Russian space agency, we're actually launching Russian rockets from French Guiana. The last project I did was Galileo. We actually launched our first 2 Galileo satellites using a Russian space agency vehicle called Soyuz from French Guiana. So there is that. In fact, I think it's a good example to world leaders to look at how space agencies, because they work together so well, and it's multinational, international level, and it's all for the cooperation of science and building spacecraft. Yes, one more. Am I familiar with the Fermi paradox? No, I'm not. What is that?
It's the paradox of if there's life outside of our solar system, then why haven't people or things contacted us simultaneously?
I think the answer to that question is, I think if they're really clever, they're probably just observing us without interfering with us. It's a bit like when we look at ants on the surface of the Earth, and we're thinking, well, we can see the ants, and they're pretty dumb, pretty pathetic compared to us, so we'll just look at them. We have no reason to disturb them. I think if there's any higher intelligence looking at us, I think they're probably just observing us and thinking, we probably won't do what they're doing, right?
Okay, at that point, I think we're going to close. Thank you very much for coming. We'll be outside if you want to talk to us on the way out. And please help me thank Warwick again.
I encourage you to smell the dishes outside, to smell what a comet's like. Okay, thank you. I'll just leave that with that. Yeah.